Yeah.
Hello, everybody. Welcome to another workshop. We're just going to give you guys some time to get into the space and get comfortable. Just give it a few moments here. And if you could help us by turning off your video, that would help a lot. Thank you. All right. I think we are good to go. Thank you, everyone, for joining us for an intro to AI on Arbitrum Stylus with Matt Hamilton. Thank you so much, Matt, for joining us. Have a great workshop.
Cool. Thank you very much. Right. Hello, folks. So my name is Matt Hamilton. I'm Senior Developer Advocate at the Arbitrum Foundation. And this is going to be a talk about a little bit about an introduction to Stylus, just to kind of cover some of the little basics about Stylus, which is a system we have that allows you to write smart contracts in languages other than Solidity. So, for example, Rust on the Arbitrum chain. But specifically, as we're talking about agents, we're talking about AI. I've put together a demo to show about how to write an AI agent actually in Rust running on the blockchain, right? So a lot of the stuff you might have seen about AI agents, a lot of it is around large language models and doing a lot of processing off-chain, because those models are so large that you're not going to really run them within a consensus environment of a blockchain. They're going to be run outside. And in a lot of cases, they're often used as a kind of an Alexa, Siri-like type sort of system in which you can give an LLM some sort of commands and converse with it, and it will then carry out some tasks, right? I'm looking at things from a slightly different point of view, and that is looking at AI agents actually running on the blockchain themselves. So these are smaller agents, but nonetheless, they allow you to actually do stuff directly within the blockchain based upon some sort of machine learning AI type model. So I'll cover that in a bit and give a bit more of an example about that. What we're going to do is just go a very quick rundown through Stylus for those of you that are not familiar, just to bring everybody up to speed. Then I'm going to talk a little bit about the AI agents that we're implementing. And then I'm going to go over to VS Code, and we'll look through some code for a demo I've written. And then we can actually sort of have a play along. Actually, I have here, let me just put in the chat. This will come up later in the slides, but I'll put it in the chat as well. That is the link to the code we'll be going through. So if anybody wants to kind of look at it in advance, that's where we're going to be. Right. So intro to AI and Stylus. So Stylus is an execution environment that we have on the Arbitrum blockchain. Arbitrum's a layer 2 blockchain off of Ethereum, and it allows you to have smart contract compiled down to WASM and run on a WASM runtime. So this is a separate runtime that runs in parallel to our EVM runtime. But as you'll see later on, I'll demonstrate, it's actually ABI compatible with EVM and with Solidity. So you can write smart contracts in Rust that can interact with Solidity smart contracts and vice versa, right? According to the blockchain, they're exactly the same. So originally you had kind of this sort of divided thing where you had blockchains that used the sort of EVM style languages, mainly Ethereum and Ethereum layer 2s that had Solidity, and even things like Viper, that's a Python-like language that compiles down to EVM. And then you had a separate sort of world of the WASM and BPF blockchains, so things like Solana, Near, Stellar, that allowed you to write in Rust or C, C++ compiled down to WASM, right? But why can't we have them all? So this is what Stylus allows you to do. Stylus allows you to combine both the EVM and the WASM runtime on one blockchain, and you have the best of both worlds. So why is Stylus kind of a game changer with this? So it opens up Ethereum. You have the network effects of Rust. So there's something like, I think it's about 30,000 Solidity developers worldwide. There's about, I believe it's about 5 million Rust developers worldwide. And if you open that up to C, C++, that can also compile down to WASM, you're up to about 15 million, right? So there's the network effects of that. Outside of blockchain, but also within blockchain, there's a lot of other blockchains, like I said already, Solana, Near, Stellar, that use Rust. And so this gives an environment where they can use their Rust skills within an EVM environment as well. But it also gives you much more computational capability and much more memory efficiency. So that is why we're able to do things like write an AI agent that could run actually within a blockchain, right? If you tried to do this within Solidity, it would potentially be possible, but it would be a lot harder to actually do and a lot less efficient. The WASM runtime is a lot more memory efficient, a lot more compute efficient. So for a given cost of gas, you get about 10 times better computation capability and about 100 times more memory efficiency. So that certainly matters when you're doing things like, say you're trying to implement something like, a neural network, and you have a large number of, matrices and variables. So, that starts to add up when you have things like that, right? So, like I said, it's ABI compatible. So on the left here, we have a counter contract, kind of like the basic sort of hello world contract in Solidity, in which you see there's a contract with a counter. It's got a uint 256 as a count, and it has three methods here: get, increment, and decrement. And on the right-hand side, we have the same thing implemented in Stylus as Rust. So we've got a macro here, sol storage, that allows you to define your storage in exactly the same way. So uint 256 count, and then we have the implementation of the actual contract, and we have again our get, increment, and decrement methods there, right? A little bit more verbose just to make it more readable there. As you can see, one of the big things about Rust is its type safety. So, you do end up having to cast things between different types quite a bit. But the good news is that you actually gain a lot of safety in that regard. So, like I said, Stylus enhances smart contracts, better performance, better security, things like type safety in there is a lot stronger, and modularity, right? You can access the whole Rust ecosystem. Rust has a thing of what are called crates, and crates are libraries that you can utilize in your smart contracts as well. So that's a quick rundown of Stylus. I went through that fairly quickly. Someone's saying, is the screen paused only for you? Don't know if anybody else can confirm. Hopefully it's working for everybody else. I'm currently on a slide, why on-chain AI. So hopefully other people can see that. So everything's working good? Okay, thanks, Aubrey. So on-chain AI, like I said, most kind of current AI stuff you're looking at the moment is off-chain computation, large language models, your chat GPTs, your Claudes, that kind of thing. And then followed by some sort of on-chain action as a result of that. In this case, what we're going to do is we're going to demonstrate a different approach, which is implementing an AI agent to run entirely on-chain. Now, you're not going to have a big billion parameter large language model, but you could still have a number of very useful applications for an on-chain agent that uses machine learning and AI. So something like, a DEX hook that analyzes market conditions real time. So Uniswap v4 has hooks. You could have something that actually analyzes the price, implements some sort of prediction based upon that, maybe a neural network. There's a thing called a Kalman filter that's often used for predicting, a true value within a number of sort of noisy measurements. You could have something like a dynamic risk scoring for lending protocols. So you could have a sort of an Aave type protocol that allows you to, lend and borrow assets, but maybe it does some dynamic risk scoring or pricing based upon some predictions. You could actually predict price for some sort of trading mechanism or, liquidity provision in a pool, or maybe some sort of automated decision making based on-chain metrics as part of a workflow within a smart contract. And you can get this all running on-chain. So the aspects we're going to look at today, we're going to look at a particular type of machine learning and AI called reinforcement learning. So the easiest way to describe reinforcement learning is a bit like training your dog, right? When you ask your dog to sit, your dog doesn't know what the word sit means initially. They don't understand English. They don't know what that means. You say sit, and maybe they run away, they scratch, they lie down, they do whatever. Eventually, they'll randomly come across, they'll sit. And you'll say, good boy, and you give them a treat, right? They then associate that treat with that action that they did. And you repeat it again, and you say sit, and eventually they learn, they associate sit with that reward, and they start to learn the process. That's what reinforcement learning is. So you have this, what's called agent environment interaction. So you have an agent that interacts with an environment and gets a reward. And I'll show you a diagram of this on the next slide. But one of the big things being is it's learning via trial and error. So most other types of sort of AI or machine learning are based upon taking a set of inputs and a known set of outputs and training a model based upon those, and then feeding it some unknown data and hoping it makes the same inferences, as a result. Whereas with reinforcement learning, you don't tell it the answer, but you kind of give it a reward for what it's doing. Again, this will make sense, hopefully, as we go along. And there's a number of different algorithms on here as well. The one we're going to be looking at is one called Q-learning as part of this. Now, if you've heard of reinforcement learning or you've heard about some of this stuff, there was actually a project called Jim that's now forked off to its own project, originally by a small company you might have heard of called OpenAI. So OpenAI had a thing called OpenAI Jim, and it was an open source repository of environments and agents that you could use within reinforcement learning, all written in Python, that allowed you to kind of test and model different algorithms. That's what OpenAI used to be doing when they were originally doing open source stuff before trying to take over the world. But yeah, so a lot of this kind of comes from that sort of background there from Jim and Gymnasium. Now, the protocol we're using here, the technique we're using is called Q-learning. So you have a game, imagine, in this example, an environment. So we've got like a grid of squares here. We've got a little robot you can see in the top left here. And that robot has to get to the end. Has to make some moves through the squares and try not to touch the bombs, the mines as they go along. So what happens is the robot basically randomly moves around, and each square you have a state stored. And there's an action that it can take. So it can move up, down, left, or right. So from each square, you have an action. And the end result is to work out which action is the most favorable action for any particular state. So if you're in any particular square, that there's a particular move that makes the most sense, right? And you could expand this state because you could include in things like, visibility around you. So you start to learn if there's a mine in one particular direction, you don't step in that direction, for example, right? So you have this iterative workflow sort of shown up here on the top right, that you have an agent, and the agent observes a state from the environment, and it takes an action. And as a result of that action, the environment gives it a reward. And it starts to learn from that reward whether the action that it took in retrospect to that state was a good thing or not. So the environment can give it a positive reward and say, hey, that was a good thing to have done. Or it can give it a negative reward, right? And say, no, that was bad. So you stepped on a mine, that's bad. We'll give you a negative result. You get to the end, that's good. That's a positive result, right? Now, I'm not going to go into the maths too much on this, but I do want to just kind of briefly break down how the Q-learning sort of main function, which is shown here. So, like I said, it's an iterative process, and each time you go around, you work out a new value of Q for a particular state and a particular action. And that involves taking the current Q values and adding to it some reward for that state, multiplied by a learning rate. So there's a couple of variables in here that you can tweak that result in how quickly it will learn. And you also add on some discount rate, and that is basically how far in advance, what priority you put on future values versus current values, right? So it might be that a very high reward at the end of this is actually very valuable versus a smaller reward closer to time, right? So that's what that model's They're that yellow and green part there, the epsilon. And then we subtract the current Q values from the end to basically normalize it there, right? Like I said, we don't need to get too bogged down in that, but that's just to kind of show you what happens. Each time we go round this loop, we recalculate that. So I'm saying that the screen we're seeing is the GitHub screen. No,
Yes,
you should be seeing slides.
I was just going to pop in and just say I kind of noticed based on what you're talking, we were seeing just the front end of the Arbitrum on-chain agent GitHub screen.
Ah, okay. 1 second, let me reshare here because has that just changed then? Because that should.
That was what we were kind of seeing the whole time. I wasn't sure. Oh, here we go. Now we're on Q Learning. We can see that now.
Okay, right. Have you seen any of these slides here, or have I been talking blankly to a GitHub repo?
Oh my gosh, I'm so sorry. We thought that that's where you
Okay.
were starting, but yes, we are
Right.
seeing these for the first time right now.
Okay. Okay, apologies for that, folks. Anyway, just to quickly flick through these, just so you see what you missed there. I was talking about Stylus, sort of house divided, why Stylus is a game changer, a little bit about Solidity versus Rust, how Stylus enhances smart contracts, why on-chain AI, talking about reinforcement learning and analogy of kind of training a dog there and giving it a reward when it does the right thing, and it associates the reward with the action. Gymnasium, which was a fork of the OpenAI project. And I was talking about Q learning here and how you would have like a grid of a game, and this little robot has to move around and it gets a score here. You have this iterative loop between the environment and the agent in which the agent observes a state, takes an action, gets given a reward. And then I was talking about the algorithm sort of towards the bottom there. Okay, so hopefully that's catch people up quite quickly here. So now what we're going to do is we will be switching over to actually some code. The link I put in the chat, there's also the QR code here for the GitHub repository that you've just been staring at for the past 15 minutes. And I'm going to show you this on-chain agent here. So we've taken that idea that I showed you before of a little sort of maze and simplified it slightly. We don't have any bombs in here, but the idea for the agent is to be able to get from the start position to the end position. And it's modeled actually as an ERC 721 NFT. So it's an NFT that can dynamically learn the solution to the puzzle, right? So again, you could do all sorts of things with this. You could have NFTs that maybe like battle against each other in some card game. You could have contracts that act as hooks on, like I said, dexes and things like that, right? So let's switch over here. Right. Hopefully you can see VS Code here and some code.
Yes.
I'm going to, good. Okay. Right. What I'm going to do is I'm going to step through the kind of the sections of this code. I'm not going to go line by line, but I'm going to go through and kind of identify the sort of key areas of the code. And then if people have any specific questions, we can talk about them kind of at the end. And then I'm going to demonstrate kind of what this does here. So like I said, this is all written in Rust here. There's a Stylus SDK and a Stylus CLI. And there's I'll give you links at the end here to download those and all the documentation and everything there. But there's an SDK that gives you various data types, and these are data types that can be emitted or can be converted into EVM encoding and returned, to and from the EVM. And there's also some storage types here that are used for storing data in the EVM as well. So we start off with a few constants here. We define the maze size, so it's going to be a 5x5 grid. There's 4 different actions you can take, move up, down, left, or right. And so the total size of our table, our Q table, this is the table that we map all of the possible moves, is the size of the maze times the action count, right? And here we've got an enum that defines the status of the cell. So it could be a cell could be empty, could have a wall, a start, or a goal endpoint. And we're going to lay out our maze. So this maze is kind of fixed at compile time. Like I said, you could make it randomly generate the maze. You could have multiple, you could have one contract generate the maze and another contract try and have an agent that solves it, for example. But here, as you can see, it's sort of 5 by 5 and a combination of, we're starting in the top left. We've got some empty cells, some walls, and the goal is sort of down towards the bottom right here. Okay. We've got 4 actions, like I said, up, down, left, and right. And we define them again as an enum just for ease here. And we've got a action kind of iterator here that can iterate through all of our actions. We can emit events, and you'll see why we do that. So this is a solidity event here. We've got a macro here, sol, that allows us to define things in certain solidity sort of fashions here. So we've got this training completed event, and you'll see the use of that in a bit. Entry point, this is a declaration here that tells us where the code should start executing, right? So this is where we start, because you don't have a main function in a smart contract. So this just tells where the interpreter should be sort of looking to start things. Storage, here's where we define our storage. So in Solidity, you'll define your storage kind of at the start of your contract. And most things will probably be something like uint 256s you'll store there. We're storing the owner, and that's an address. And we have our Q table, and that is an array of 32-bit integers. So again, this is where Stylus and Rust can be more efficient, because you can store 32-bit integers. In Solidity, it defaults to uint 256. Yes, you can use smaller values, but it then kind of pads them out and packs them in a certain way, and you can end up with very inefficient storages. This does it in a lot more of an efficient fashion here. And the size of that array is Q table size. Now, you could actually you can see here originally, I actually had it as a 3-dimensional array here, a storage array within a storage array within a storage array. But actually, that made things a lot more complicated in the process here. So I decided to flatten the array out and just make it Q table size here. And we've got a uint 32 for a random number generator seed. So I've got a very simplistic random number generator here. If this is in production, you'd want to replace it with something that actually produces much better randomness. But that's what we're using here just for this demo. So we start our contract here. Now we've got 2 sections here. We've got these implementation blocks here. One is marked public, and then later on, if I scroll down just to quickly show you before I'll come back up again, there's another one later on which has our private functions in. So the public ones will be the ones that get exposed via the ABI. So those are the ones you'll be able to call from within Solidity, right? So we've got this supports interface method or function. This is actually part of ERC 165. This means that other systems can work out what kind of smart contract this is, right? If you use something like the Open Zeppelin libraries, and Open Zeppelin actually do have Rust implementations of their standard ERC 721, ERC 20, etc. Libraries, you can use those. They've got Rust versions of those as well. But in this case, I'm not utilizing any other third-party libraries. I'm doing this from scratch. So I had to put a bare bones implementation of this in, just so that wallets know that this is actually an ERC 721, and we have ERC 721 metadata. And again, you'll see why that is later on, because I'm going to load this ERC 721, this NFT, into MetaMask, and you're actually going to see it in MetaMask as well. We have a mint function. Again, similarly, if you've done anything with ERC 721, this will be familiar, and we mint it to an address. Here we set the owner's address, and we set our random number seed. We're just seeding it from 1. We could probably seed it with something else each time, but there we go. We've got a symbol and a name here. So it's the symbol of this token is called QMaze. It's got a name and it's got a description, right? Again, in Rust, you'll probably spend a bit more time than within Solidity doing things like converting types. So here we've got to actually say this is a string type, and so we're calling toString here, right? We've got a balance of function, and with this NFT, there's only one token, right? Most NFT smart contracts allow you to have a collection of tokens, and there's a mapping that maps from a token ID to a holder. In this case, for simplicity's sake, we just have one, right? So if you ask the balance of the owner, then you get one back. Otherwise, you get zero back, right? So the owner can own one of these and nobody else can, right? Again, this is just to simplify things for this demo. And as you can see, we're returning this as a uint 256. That's just because that's what most third parties are expecting it to be. They're expecting it to be a uint 256. And the method signature of this gets generated within EVM as a hash of the method signature. So you need this, you need the values to be the same as what you would normally have in Solidity. Otherwise, you're going to get a different method signature, and certain things might not be able to find it then. We have this owner of method. Again, we pass in here a token ID. If the token ID is not 1, then we return this as an invalid token, right? If it is the owner's address, we return OK. If the owner is 0, i.e. it's not been minted, then we return an error as well then, right? So that's kind of the sort of standard ERC 721 kind of boilerplate we need in order to get this to work within a wallet, right? Now we're going to get onto the actual AI stuff that we've implemented in here. So we've got this function get queue table, and that will return our table that we have here, and it gets it will get the table, and it basically will return this back to you as an array here. So this allows a what am I trying to say here? This allows us from outside, from the ABI, to get the queue table to use for debugging. And again, I'll show you this because we're going to load this up actually. Although we're going to compile it in Rust and deploy it with Solidity, we're going to access it through Remix, and I'll show you that in a bit. Now we get onto the AI side of stuff. We have our train method, and we pass in a number of parameters here. So number of episodes, the number of iterations we're going to do with training, right? So this is, you know, how many times you try and sit down with your dog and try and get them to sit and give them a reward. The number of steps, so how many times you try doing that until they get it right. And then we have these 3 values, epsilon, alpha, and gamma, and they are, like I said earlier on, how quickly the learning function converges, how much it prioritizes new information over old information that it's learned, and how much it prioritizes a future reward over a reward sooner. So we start off with, we get our start position. We've got a method that will just iterate through that hard-coded maze and return our start position. We have a random number seed here, and then we start looping through. So we have a number of episodes we want to loop through. Our current position is the start. And for up to a maximum number of steps, we decode our current queue table. So this is on our table, we find what position we're in and what are the values that are available to us there. So in this case, remember, we can move up, down, left, right. So there's 4 values that we could return back. And this basically gives us the current preference for each of those, right? And the idea is we want to find the move that gives us the most reward, right? So of those 4 values, we're going to try and work out which is the highest, because that's the one that gives us the most reward. And we call this method choose action, right? And that will then choose an action based upon that. We'll cover that down in a bit. We get a new seed out of that. We put that into our random number generator just so that we've got a new seed for next time. And we actually store it. This is something you'll see here. With these storage types, you have to explicitly set the value. So with Solidity, you don't need to actually call a set or a get on a storage type, but with here within Rust, you do here. So we're storing that explicitly. We calculate our next position. We've got a method here. Again, we'll cover these in a bit, that gets the next state, gets a reward, decodes a Q value, works out what the maximum reward is, and then matches the action up, down, left, or right. And then we're going to calculate the change in our reward here. And again, this is I'm not going to go into the mass of it, but this is basically the encapsulation of that equation that was earlier on the start on the slide towards the start here. It works out the current Q values. And we then encode and store those back again, right? So this is one loop around in which we are basically working out, okay, what is our next move and what is the reward we get for that move? If we get to the cell called goal, then we've hit the end and we break out of this. And once we finish going through all of this, we're going to emit an event called training complete, right? So that's the loop we go through. Now we have a method here called token URI, and token URI is you give it a token ID and it will return back some JSON for the metadata for your NFT, and also then a link to the image data. In this case, we're actually going to generate a SVG, a dynamic SVG, and return that within the image data. So we're not returning a URL to a IPFS CID or some HTTP location to load, say, a PNG off of somewhere. We're actually generating this image within our code here. Now, again, I'm not going to go through too much through this, but this is some code that basically builds up our SVG to visualize it, and we'll see this in the output of this in a little bit, right? So this visualizes what our maze and state looks like. We get all of this, and we output some JSON there as metadata, and we include in there our data, and the whole thing gets returned as a data URI, right? This is a URI that instead of being like HTTPS and then a location, a data URI contains the actual data base 64 encoded in there. Okay, hopefully I don't have the chat here anymore. Hopefully people are. I'll catch up with this in a bit here and see. There seem to be a few comments in here. So let's see here. Right. We've got a number of, like I said, methods here that check things like if this is a valid position, reward, et cetera, choosing a value here. You can go through all of this. Then we've got some helper functions here. So base 64 encoding the data, right? So as we're kind of getting on for time here, what I'm going to do is give a quick sort of demo of this and show what we can do with this, right? So we can run a command cargo stylus check here, and it will go through, compile it, and check that everything's okay. And at the end here, we see we've got contract size. Everything was all good here. It tells us the WASM size. There's a few warnings I've got to tidy up on the code, but otherwise it's all good. I can also go ahead and deploy it. So there's a cargo stylus deploy command, and I pass it my private key, tell it which network to deploy to, and it's gone ahead and deployed it. So we have here an address where our code is deployed. So you can go and look this address up on Arbiscan, and you will you will see it there. If I go and actually look on Arbiscan, you'll see it there. But what we're going to do is we're going to take that, and we're actually going to load it into Remix, right? You might have used Remix for Solidity code, but one of the things you can do with Remix is you can actually load the ABI in from something else. So this ABI here I've got, this is exported. So I can do here, here, there's an export ABI command here. Don't worry, that private key is just for a test account. I don't have it here. So, but there's an export ABI command that will export the ABI as JSON, and then you can put it into into Remix here, and I can tell it to load the contract at the address we just deployed here. So I can say load that. It will say okay, and we have our contract here, and I can now interact with it directly here. So I can mint it directly here. So I'm going to take my address here. I'm going to copy this. You may not, I can never remember whether you can see that or not. I think you can see that. Mint, and I can hit mint. And I just need to approve that. That was off screen. So that was MetaMask popping up and asking me to prove it. And it's gone through and it's okay here. So we've now minted it. And I can actually look and say, okay, who's the owner of token number 1? And it'll come back with my address. I can take my address and I can put it into here and say, what's the balance of? And I've got 1. I can look at sort of things like the symbols or whatever. Now, remember, I put this get queue table in. I can call that, and you can see the table is zeros. There's nothing there. And I can get the token URI. If I call that there, that is an encoding of all of the data. So if I take this contract address, and I've created a simple little web app here that I can put that in and hit view NFT. And that's going to run. And here we have the output. Now, we haven't trained this yet. So the Q table is all zeros. And so as far as it's concerned, to get from the green square to the red square, you go up, which is obviously wrong. It's not going to get anywhere. So let's try and train it. Here I can bring up the train method here, and I can say, okay, let's train it for 20 episodes with a maximum of 20 steps. And we're going to learn, actually, let's do 10 episodes to start with. Epsilon of 20, alpha of 30, gamma of 90. So those are, again, those are the parameters. I'm not going to go into, again, too much detail on them, but those are the parameters for how much it learns. And then if I hit transact, MetaMask is going to pop up again on my other screen, ask me to confirm it. So you can just see, maybe see there, it's confirming it. This is all happening on Arbitrum Sepolia. You can hit confirm and watch what happens with this NFT viewer. You'll see training is completed, it updates, and you see some of the values have changed. So it started to try and learn. Now, it's still not learning very well. It's still starting from this green square and going up, which is obviously not going to get anywhere. Let's try another 10 rounds of learning. So if I hit transact again, I can do that, hit confirm, and it'll go through and it'll learn a bit more. And it'll come back, and it's not learned to get any better there. Let's train it for more. Let's train it for 30 episodes. And if I hit get Q table, you can see this is starting to change in values here. So let's try 30 episodes. Get to learn a bit more. Confirm. Now we're getting somewhere. So we go down, right, down, right, right, down, right. So it's solved it, right? It is learned now how to get to the end of the puzzle. So again, this is all happening on chain. And I hit, get Q table. You can see here, this is the scores. And for each one of these squares, there'll be effectively a score as to whether you should be going up, down, left, or right. And the highest value is the route you should take. And over time, if I kept training it, that number would get higher and higher when it becomes more obvious that this is the right way to go. So the more confident it gets in the route to go. But as you can see, it's solved it. Down, right, left, right, 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 down, 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 left, and it gets there. So there we go. Now, just to show you, I can actually load this up into MetaMask here. I can go in. I'm going to delete this old one I had here. But I can import in, I can copy this address, and I can go into MetaMask, NFTs. Can you see my MetaMask? Hopefully you can. And import. Successfully added. And there we go. We have the maze there. And as you can see, that's loaded that same value. Now, MetaMask, unfortunately, doesn't update that value, it kind of caches it. So as we train it, you won't actually see that move. You'd have to delete it and re-add it again in order to see that. That's why I created this little web app, just so you can actually see the progress going on. But as you can see, we have an NFT here, ERC 721 NFT, dynamically returning an image, and it's a result of a training process completely on chain. Remember, this training has happened completely on chain within the transaction on Arbitrum. So nothing is off chain here. And like I said, you could use this for getting a smart contract to learn various behaviors depending upon what's happening on a blockchain. A price does something, it learns to do something in response to that, for example. So that's kind of that with the demo. So I'm just going to quickly flick through here. If you need help in the hackathon, there's a couple of things. There's a Stylus showcase, and that Stylus showcase, there's some builders that are kind of talking about what they're doing. So that's a bit more kind of like inspirational stuff rather than sort of deep technical stuff, but a bit more about some builders that are building on Stylus. We have the Rust Stylus SDK. You can find in Off-Chain Labs' repository. We have a site called Stylus by Example that gives you some help there as well. And like I said, OpenZeppelin have done their standard contracts in Rust. And that's great. I learned a lot from going through these when I was trying to work out how to do something. I could go and look and see how they'd done it in their library there as well. We also have the Stylus Pro series, and two of my colleagues that are over at Off-Chain Labs, Jose and Crisco, go into a lot more detail on things like debugging and unit tests and stuff like that for Stylus if you want them. They're all on YouTube. And we have a Telegram and a Discord channel as well. So obviously for this, there's the Discord channel for ETH Global. I recommend you ask in there. But there's also the Arbitrum Discord channel, and there's a Stylus Devs channel on there. And there's a Stylus Devs Telegram as well as the Discord channel there. So thanks very much. My details are there. That QR code will probably take you to the wrong presentation because I haven't updated that. But I'll put the link to this slide, these slides in the Discord, the ETH Global Discord. So, right, any questions here? I know I've probably gone on a little bit over time. Just looking through the chat here to see.
Do you see someone waving for a potential question? Or they were just saying bye. I'm also lucky for you, Matt. I do edit our videos, so I'll be able to sync your slides with that first 10 minutes there.
Oh, brilliant. Okay. Thank you. Great. Okay, then. Well, thanks a lot, everybody. And like I said, in the Arbitrum channel, Arbitrum partner channel on the ETH Global Discord, you can get help there over the next couple of weeks. I look forward to seeing what you build. So good luck with it, and yeah, get building. Thanks a lot.
Thank you so much, Matt. That was a workshop called Intro to AI on Arbitrum Stylus with Matt Hamilton. Thank you so much. And ETH Global, we are good to end our stream.